So, hello, we are now in the second class of the 6th week. Just so you know, Zoom, I'm going to show you just so you can see what I'm talking about. I'll start sharing. And when I go to, where is it? When I go to, oh, there it is. So this is me trying to upload a Zoom class. And it's been going now for a couple hours. They take a very long time, and half the time when they're done, they get an error message. So not every class is up because I'm trying and trying and trying, and sometimes it's just without success. But I'm trying, and slowly but surely they're going up. So whatever classes we need will hopefully be up as soon as it lets me. So it's going very, very slow. I'll keep checking in, as you can see, and we'll monitor its progress. This is a meeting that I'm currently downloading. This is where it's up to. So we'll try back in 20 minutes and we'll see what progress we've made. Okay, so let's recap chapter 15, what we've done so far. As a lead into 16, we'll do some examples. It'll be lots of fun. Let's get started. So, I got a couple texts here. And people are saying, they load faster during the night, Professor. Well, I tried during the night as well. And that hasn't been working very well either. Are we not getting PowerPoints from now on? That's correct. There are no more PowerPoints. And to be honest, I'm teaching 8 classes and do not have time to make my own, unfortunately. So from here on out, it'll be good old-fashioned teaching. We will use the ebook, and it's almost as good as the PowerPoint, but not quite. So we talked last time about the difference between any updates on the monitor. Oh, you mean the dock camera? I haven't had a chance yet to try. I'll be working on it this weekend when I have a few hours free. And during the week, I'm packed solid, one thing after the other, and I'm just behind. I'm sorry. So I'm trying, but I'm not quite there yet, so I don't have an answer for you. But hopefully it'll be there next week. Anyway, so parameters and statistics. So in life, there are certain things that we do not know with certainty, but we would like to know for whatever reason. An example might be the average weight of every American. Maybe we're checking on whether or not there really is an obesity epidemic and people are getting heavier year to year. We might want to do a time plot of average weights of every American, maybe every year for the last 20 years, whatever the case may be. But we can't ask everyone. There's just way too many people. So we take a sample and we try to use a sample to draw conclusions about the entire population. The average weight of every American, that's a parameter. Why is it today's a pizza. Speaking about getting fatter, today is pizza. But anyways, so the parameter is the average weight of every American. Why is it a parameter? Because it's a number that describes the entire population. Yes, I got you. It's a number that applies to the entire population. We cannot know it. There's just too many people to ask. So what do? We take a sample. The sample, the value that we get from the sample is a statistic because it comes from a sample. What we want to do is use that statistic to make some inferences about the population as a whole. Is the value of our statistic close to the value of the parameter? Is it not close? How confident are we that we're close? These are questions that we might want to ask. So we had a few basic properties And the first one was the law of large numbers. A very important law. It says that if you draw observations at random from a population, as the number of observations drawn increases, the mean of the observed values tends to get closer and closer. What's wrong?
Where's the other place?
It's underneath.
Oh,
Closer and closer to the mean of the. I'm teaching. Yeah. I'm still eating this one. The whole pizza here.
okay.
It gets closer and closer to the mean of the entire population. Okay, so sorry about the interruption, but you have the sample average X bar, and the sample average X bar is your guesstimate of the parameter mu. Okay, that's no problem. So it's your estimate of the parameter mu. How do you get a better and better estimate? You get a better and better estimate by taking larger and larger sample sizes. The larger your sample size is, the better your estimate is going to be of the entire, no, where is it? Oh, same place. The better your estimate's going to be of the parameter. That's the law of large numbers. The larger your sample, the closer X bar is going to be to the true value. That is one of the three important concepts from this chapter, the law of large numbers. We also saw last time that when you have a distribution, your population distribution, it's going to have some shape to it. Maybe it'll look normal. Maybe it'll look not normal. We saw ones here that have decidedly not normal shapes, but I don't know where they are. They're on a different slide. But whatever it is, we saw an applet last time that had all different shapes of distributions. Those shapes we're taking one at a time. Maybe it was like this, maybe it's like one of those weird looking ones, or it's high here and low here and medium here. We had all different types. But what we saw is that as you take more than one at a time, 2 at a time, 5 at a time, 10 at a time, the shape changes. And we saw that no matter the starting shape, if you take a lot at a time, then what do those shapes get closer and closer to becoming? What did we see last time? Anyone?
Can you repeat the question again?
So last time we saw an applet. And on the applet we saw that no matter the shape of the original distribution, if we take samples of size 2, 3, 5, 10, 20, 30, the shapes changed. And they got closer and closer to being what as the sample size got larger and larger? Bell shape.
Normal distribution.
Normal, right? That is the central limit theorem. That no matter the shape of the distribution that you start with, which is the population distribution, as the number or the size of your sample gets larger, the distributions get closer and closer to being normal. We saw that with, just doing it again, central limit theorem, applet. So we saw here a decidedly non-normal shape. You take 2 at a time. You take 3 at a time. You take 4 at a time. 5 at a time. And as the number gets increases, the shape continues to change. But as n gets larger, it looks more and more normal. These are all simulations. You can see already by 10. If I just gave you this shape and said, hey, what shape is this? I think everyone who knows about statistics will say, oh, that's normal. Even starting something like this, very, very right skewed. You do 2 at a time. You do 3 at a time. Still got some right skewness there. You get to 5, still right skewed. You get to 8, let's say. even by 8, it's already looking normal. Okay, so the central limit theorem says that as the sample size increases, the sample distribution shape looks more and more normal. But the point of this section is that every size has a different shape. Size 1, the original population, one at a time, will have some shape. And as the sample size changes, the shape is going to change. So you have the population distribution, which is looking at one at a time. And then you have a sample distribution, which is samples of a given size. So 5 at a time, or 10 at a time, or 100 at a time, and so on. So if the original distribution is normal, if the individual observations are normal, then the sample mean is normal. Although what happens, while the mean stays the same, the sigma, the standard deviation, gets smaller. It gets skinnier. Can you repeat sampling distribution again? If I take one at a time, one data point at a time, that is coming from the population distribution. The population distribution says how many are here, how many are here, how many are here, how many are here. So if I take one, where's it most likely to be? But if I take samples of size 2, of size 10, of size 100, whatever the case may be, if I take samples and I say where is the average of my samples going to be, then the amount here or the amount here or the amount here and so on is different. The sample distribution looks different than the original distribution. Every size sample will have its own shape. The central limit theorem says as the sample size gets larger, that shape resembles more and more. You take an average of a sample of the population. Yes, if think of the original population, where does the histogram come from? I take 1 million observations from the original population. Some are here, some are here, some are here, some are here, and that's where the distribution shape comes from, because I have a bunch in each area. Well, if I take the same sample but 2 at a time, and I do their averages, some averages are here, some averages are here, some averages are here, and I'm going to have its own histogram, its own distribution shape. It's a different shape when I average 2 at a time, 3 at a time, 4 at a time, and so on, than if I just do 1 at a time. The population distribution is 1 at a time. The sample distribution is more than 1 at a time. Why is it impossible? I mean, I could take 100 observations and consider them each individually without averaging anything. Just say how many are here, how many are here, how many are here. It's okay. Right? And then if I say, take the same distribution but do 2 at a time and average pairs, I can see how many are here, how many are here, how many are here, how many are here, and so on. I can do it for any size. And the point is that sample distributions are going to look different than the population distribution. But if the original is normal, then each of the sample distributions are also normal. Once a bell curve, always a bell curve. The only difference is that the spread, the width, is going to be skinnier. Because as n gets larger, the denominator gets bigger, and when the denominator gets bigger, this whole thing gets smaller. So rather than having a width of sigma, it's going to be sigma over the square root of n. It'll be tighter. It'll be more sharply focused. The central limit theorem says what I just said, that it makes no difference what the underlying population is. It will eventually be normal if the sample size is large enough. What is large enough? As a general rule, 30 or more. If you have 30 or more, even if the original distribution is not normal, you can use the mathematics of normal situations for your sample distributions. So that was a review of last time. And I wanted to go over some of it again. And I wanted to do some problems so that we can see these in action. So let's start out with number 19. So go ahead and read number 19 to yourself. isn't that a problem that the original distribution is not normal? Not really. Not if the sample is big enough. Weston, I'm not sure what your question is. Can you ask it verbally?
Yes, I can. So isn't that a bit of an issue if the sample, where we keep taking, larger and larger samples, and we always get a normal distribution, and the actual original, the original data, if we could see it as a whole, was not a normal distribution curve? Do we not lose information about the actual data? Say if we had a supercomputer that actually did have the average height or weight of every American, and we compared a sample that gets close and close to a normal distribution, even though the original data is not a normal distribution. Is that not an issue of us losing data?
No, because remember what we're calculating. The histogram that we end up with is just where we expect the average of, let's say, 50 at a time to end up. If I have an idea of where 50 at a time end up, that's not going to help or hinder the fact that I don't have an idea where one's going to end up. So in other words, it's not that I lose information. I think it's this information that I never had. If I never had the original distribution, then, well,
say if there was no one in America that was 6'2", it all fell, on either side, and for some reason there was no one that was 6'2".
Okay.
And if we took a sample size and say we have taller Americans and the average was 6'2", wouldn't that kind of throw us off a little bit with our sample size that kept on looking like a normal distribution where 6'2" is the average? But
well, we're not. Remember what we're looking at here. The sample distribution is not our conclusion about the original. The sample distribution just tells us where averages are most likely to end up.
Okay.
If averages are most likely to end up at 6'2", it doesn't mean that individuals are most likely to end up at 6'2".
That makes more sense.
It's just that the averages are more likely to be here.
Yeah, since we're not drawing conclusions, then that seems perfectly okay.
We're not drawing conclusions about individuals. We're just drawing conclusions about averages.
Thank you.
Okay. So in this question here, number 19, it says scores in the critical reading part of the SAT exam in a recent year were roughly normal. That's key. Basically, it means we can use normality with mean 495 and standard deviation 118. You choose a simple random sample of 100 students and average their scores. And you do this many times. So you get an average of 100, and then someone else gets an average of 100, and you do an average of 100 again, and someone else's average of 100 again, and someone else's average of 100 again, and you get lots and lots and lots and lots and lots of averages of 100 scores. And then you average those averages. So you're averaging the averages that you got from taking 100 at a time. What is the average of your average score is going to be? Is it A, 495, B, 495 over 100, or C, 495 over the square root of 100? So we can pretend this is like before, A, B, or C, right? I'm going to give you guys a couple seconds to think about it, and then we'll look at the answers. You guys see the chat, by the way, or just what's behind it? Do you guys see that as well? I'm not sure what you see when I'm sharing my screen. Do you see this chat that I get from students?
Yeah.
Okay. Yes, no. Okay, well, that's interesting. So what they're doing is we're taking averages of 100 at a time, and then we want to know what the average of those averages is. So for example, if you take 100 students, each of whose average is 495, and you average them, and then I do that, and someone else does that, and he does that, and she does that, and they do that, and we all do that, and we average all of our values, what are we going to get? So on the count of 3, you have 5 options. It's either A, B, C, I don't know, or I just don't care. So on the count of 3. Wait, that's not 3. That's 0. You can't do 0. I said the count of 3. So A, hold on a second. So 1, 2, 3, go. Okay, we got lots of I don't knows. I love I don't knows. That means we get to learn a bunch of A's, a bunch of C's, no B's, which is kind of nice because there's no formula that says divide by the number of students. There's only a formula, thank you, that says, only a formula that says divide by the square root of the number of students. So I can see why someone might say the answer of C. I can see why someone says I don't know. That's great as well. That means you don't know. But unfortunately, the answer is A. Where from the question could they tell that you're taking an average of an average? Because they say the mean of the averages, and a mean is an average, isn't it? Isn't a mean an average? When I say find the mean, I say find the average, right? So it's the mean of the averages. It's the average of the averages. So the answer is A, 495. And the reason why it's A is because this dividing by the square root of 100 part, square root of n, is how you find the new standard deviation. We don't divide by the square root of n to find the new mean. In fact, if you look back at this slide right here, it said that if the original mean is mu, then the sample mean is the same mu. If the original one was 495, then the sample one is 495. If the original sigma was 118, then what is the new sigma? Well, that's the follow-up question. All right, so this is A, 495. And at the same question, if the original sigma was 118, then what is the new sigma? Is it A, 118, B, 1.18, or C, 11.8? So by the count of 3, 1, 2, 3. So I got lots of C's, got more C's, got an A, uh-oh, got a B. So the answer here is that the new standard deviation is 11.8 because you take the old deviation, which is 118, divide by the square root of n is 100, divide by the square root of 100, which is 10. 118 divided by 10 is 11.8. So again, if the original one is normal, then the mean stays 495, still 495, but the deviation gets smaller by a factor of over the square root of n. Let's look at 21, because 21 introduces a term that I have not yet used. So let me define it. 21 talks about something called a biased or an unbiased estimator. So let me ask you a question. Suppose I want to estimate the average height of every American. So I'm going to use an estimator, something that estimates. I take 100 people, I compute their heights, and then I say, okay, I'm going to use the tallest person in my sample as my estimate for the average height of every American. Would you say that I will most likely get a value close to the true value? Again, take a sample of 100 people and say I'm taking the largest person in that sample to be my estimate for the average height of every American. No, it is biased towards one side. It is more likely to be higher because I'm taking the tallest. It's an estimator. It's just not a very good estimator because it's biased. However, if I say I will take the middle height of those 100 to be my estimator for the average height of every American, is that likely to be a good estimate? Take 100, take the one right in the middle. Assuming my sample is good, why not? It's no more likely to be taller or shorter, right? It's right in the middle. It's an unbiased estimator. We like unbiased estimators. In a more advanced class, you might talk about what makes one estimator better than another, even when they're both unbiased. Sometimes biased estimators can be good in different situations. We're not getting into that. In this class, the idea of a biased estimator is that if I use it as an estimator, I'm not going to be close to the true value. Whereas an unbiased estimator, if I use that as my estimator, I will be close to the true value. So let's look at 21. A newborn baby has extremely low birth weight, ELBW, if it weighs less than 1,000 grams. A study of the health of such children in later years examined a random sample of 219 children and saw that their mean weight at birth was 810 grams. It's claiming that this is an unbiased estimator of the actual average because it's a mean. Means are unbiased. They're exactly what we expect, right in the middle. What does that mean? Is it A, B, or C? Now, each of A, B, and C illustrates one of the three main ideas in this chapter. One of them is the idea of unbiased estimators. One of them is the law of large numbers, and one of them is the central limit theorem. So A, B, or C, the question is which one is which? Is A either the idea of an unbiased estimator, the law of large numbers, or the central limit theorem? And B is which of those three? And C is which of those three? So take a minute and think about that while I finish my pizza. Okay, who here would like to take a gander as to which of them is, let's do the easy one first, or what I think is the easiest one. Which of them is the law of large numbers, A, B, or C? Go. Excellent. Everyone's guessing B. It's fantastic. As you take larger and larger samples, your sample mean will get closer and closer to mu. That is the law of large numbers. Wonderful. Which one of these is the central limit theorem, A or C? Awesome. Central limit theorem says if you take many samples from a population, it will have a distribution that is close to normal. How do I know that? Why will my sample distribution be close to normal? Because how big are the samples here in this problem? What is the sample size?
219.
219. Is that bigger than 30?
Yes.
That's why. All right. If the sample size is larger than 30, then the sample distribution is close to normal. Well, by process of elimination, that means that unbiased means must be A. That if you take samples from the population, the average is going to be close to the true value mu. All right. That's exactly what unbiased says. That if you do lots and lots of samples and keep taking the tallest person, the average of those is probably not going to be close to the true average. But if you take lots and lots of samples and take their averages and average those, it probably will be close to the true value. That's the law of large numbers. So let's do some ones that require a little bit of math. So how about we do number 27. So the question says, almost all medical schools in the United States require students to take the medical college admission test, the MCAT. To estimate the mean score mu of those who took the MCAT on your campus, you will obtain the scores of an SRS of students. The scores follow a normal distribution. And from published information, you know that the standard deviation is 10.4. Suppose that, unknown to you, the mean score of those taking the MCAT on your campus is 500. Why is it important that it's unknown to you? Because if you knew it, why would you take this? Why would you do anything? If you have the answer, you have the answer. The whole goal is to figure out what the mean is. If someone says, hey, it's 500, you're like, great, I'm going to go play a video game or something. I don't need to do this. So you don't know that it's 500, but it happens to be 500. The question is, if you choose one student at random, what is the probability that the student score is between 495 and 505? Somebody give me a strategy for how to do this. If you take one student at random, what is the probability that the student score is between 495 and 505? How do I do that? Anyone? Euler? Taking the z-score. Well, that's one way of doing it, for sure. I think there's an easier way. But could be the z-score. Nothing wrong with that. Anyone? The 68, 95, 99.7 rule. With a little math. Well, unfortunately, this rule is only useful if you know how many deviations out you're going. But when I go from 500 to 495 and 505, that is not 1, 2, or 3 deviations. So unfortunately, I can't use that one. Where are we at? Uh-oh, we got an error. That didn't work. Oh, well. So who else thinks something else? Anyone else have an idea of how to do this one? All answers will be looked at and analyzed. No judgment. I don't know. I love that answer. I don't know. It's very honest and blunt. I love, I don't know answers. So I'm going to go to my calculator. And I'm going to go to my normal CDF. And I'm going to plug in those values. I want to calculate the probability from 495 to 505 when mu is 500 and sigma is 10.4. And when I scroll down and hit enter, I get an answer of 36.9%. If we use the websites, which websites? Oh, just some random Google website. Yeah, you put between 495 and 505, where the mean is 500 and sigma is 10.4. More pizza?
There's still one more piece, a small piece left, so
Okay.
take your time.
I'll take my time. What is the name of that website calculator again? What kind of pizza? I think it's DiGiorno's, you know, the one you buy in the, you know, in Ralph's or something, you know, in the box. You know, the square box with a circular pizza that has some triangle shapes. No, it's not the meat deluxe one. I'm a cheese man. I just like cheese pizza. Anything else on pizza is just a blasphemy and an abomination. Well, that's fine. My, there's three words in the English language that I've never said in conjunction. I am full. So I am always hungry. So if I'm hungry, it's only fair that you're hungry. Period. That's right. Calzones are good. I love calzones. Calzones are great. But hey, don't get me far afield. Come on, we're on this question. Does anyone still not sure about how to do that first part A? Either conceptually or specifically, either on the computer or the calculator. Because I got 3 I don't knows, and I got nobody saying what the answer was. Please show the calculator. Okay, I can do that. It's just a normal distribution calculator. You go from 495 to 505, where the mu is 500 and sigma is 10.4. And yes, you should get 39.6%. Or is it 36.9%? What did I get again? 36.9%, not 39.6%. I forgive you. All was forgiven here. Okay, now go to part C. What is the probability that the mean score of a sample of 25 students is between 495 and 505? You're not doing one at a time. You're doing 25 at a time. And you're taking the average of those 25. The question is, what is the probability that the average of those 25 is between 495 and 505? Do we think it's going to be the same? Wait, no, we didn't do B because we don't really need to do B, as you'll see in getting C. I don't want you to do B because that'll kind of give away some of how to do C. So the question is, what is the probability that the mean score, would you just out mean as 25 and SD is the same? What does that mean? Would you just out mean? Would you put mean as 25? No. The mean 25 is your sample size, not your mean, not your average. This is good, actually. To join us. I approve. What is the mean of your sampling distribution? What did we say before? We had like a box. Well, was that for the mean or for the deviation? Weston. So what's the mean, I ask? Yeah, the mean's still 500. The mean does not change. So when I go to the normal CDF, the mean is the same, but what's my sigma going to be? Yes, the sigma is going to be 2.08. Can you explain why, please?
It's because you do the sigma divided by the square root of 25.
Awesome. Square root of 25 is 5. The original sigma 10.4 divided by 5 is 2.08. And when I do exactly the same math, I get a very different value. 98.4%. So while one person can pretty much land anywhere, has a 37% chance of landing in there. Nope, not inverse. We're not doing inverses. Inverses go from probability to numbers. We're going from numbers to probability in both A and in part C. The only change is my sigma got smaller. That's exactly it. The only change is that your sigma got smaller. Nothing else changed at all. So if you look at the answers, the first one, what do we get? 36.9%. And the last one, we got 98.4%. Numbers are a little off because of rounding, but those are the answers. Does that make sense? Are there any questions on that? Because this is the main idea of this section, the difference between the original distribution and the sample distribution. The only difference is you keep the mean the same, but you divide the sample distribution by the square root of the sample size. Then you do exactly the same techniques. Number 37. Go ahead and read, please, number 37. So, to estimate the mean score mu of those who took the MCAT on your campus, you're going to obtain an SRS. You happen to know that the scores are normal with a deviation of 10.4. So at this point, what you have is we know it's normal with a deviation of 10.4, but you have no idea what the mean is. So this is what you have at this point. Normal, some mean, unknown, deviation 10.4. Now, when you ask someone or somehow obtain the scores of someone who took the MCAT, if you do one at a time, their answers can be anywhere, right? They're most likely to be near the center, but they can really be anywhere. So what do? You take samples of given sizes, because you know that the larger the sample size, the tighter the curve is going to be, and the more likely you are to land near the center, near the mean. So the question is here, forget about part A, let's ignore that, just part B. How large of a sample do you need to reduce the standard deviation so that it is no more than 1 point away from the mean in either direction? Because if you look at the fourth line of the question, you want your sample mean to estimate mu with an error of no more than 1 point in either direction. You want this to be so skinny that there's a 99.7% chance, I guess we should do A, right? We want a 99.7% chance that you are within 1 point of the mean. This has got to be so skinny that 99.7% of the data is within 1 point of the mean. So it would look like this. Right? You start with your normal distribution, and then you make your sample size so large that it gets so skinny that 99.7% of the data is right next to the mean, with 1 point away. And the question is, how large of a sample size do you need for that to happen? So we know that 99.7% is 3 standard deviations, right? That's definitely a key to this question. Okay, I want 3 standard deviations to be no more than 1 point away. So what equation can I write down that I would then solve for that to happen? What equation would I write down? We got to do a little math here. You can't just see the answer in your head. You got to do some math. So what Think about it. All right? Think about like a homework or 31.2. What's 31.2? Oh, I see. You took 10.4 and multiplied that by 3, didn't you? Well, first of all, 10.4 times 3 is 30. Yeah, it is 31.2. That is wrong, but I like what you're thinking. You're certainly thinking something that's correct. It's just, it was wrong. It's true. But your thoughts are certainly in the right direction. Your mistake is the fact that you're thinking that the deviation is 10.4, but the deviation is not 10.4. What's the standard deviation in this example?
You said it's not 10.4?
Nope. Why isn't it 10.4? That's a great question. I mean, it certainly says it is 10.4, doesn't it? Or does it? I'm lost. Well, Kiana, answer this question. What is the deviation as written on the 4th line of this problem?
It's a normal, the standard deviation is 10.4.
Is that the deviation for the population, or is that the deviation for a sample distribution?
I'm going to guess, I'm going to say sample. No, population, because we're looking for the sample.
We're looking for the sample. We don't have a sample yet, right?
Okay, yeah.
So the published information is about the population.
Okay.
Okay, but we're taking a sample. We just don't know the size yet, but we are taking a sample. When we take a sample of size n, what does the standard deviation become for our sample? Does it remain 10.4?
Oh, is it the thingy with the, sorry, this is, sorry,
No.
the square root of that thing?
Well, maybe.
Sorry,
So,
I'm not descriptive.
okay, no, your words are great. Thingy is definitely a technical term. So, what is the standard deviation of our sample? Is it still 10.4? So what is it? You forgot the equation. It's like the only equation we had in this chapter. How do you forget the equation? The one with the square roots. So what is it? The one with the square roots. You forgot to write it down. Oh, the horror, the horror. Come on, someone tell her, tell me, tell everyone. What is the formula for the standard deviation of a sample distribution? Anyone? So, what is the answer? It is the old distribution divided by the square root of n. That is the new standard deviation, the old standard deviation divided by the square root of n. That is the formula.
Wait, so we just leave n there?
Well, we don't know n yet. Until we know n, you got to leave it.
God. Oh my God.
No, n's not 25. Look at the question. How large of an SRS do you need? Bro, I need an anvil. I always find that studying math just clears up my headaches. Isn't that how you guys feel? So we do not know n. If we don't know n, we can't do any better than this. The standard deviation for us is 10.4 over the square root of n. Now, how many standard deviations do we need? N is the SRS of the population. I don't even know. What does that mean? No, we do not. But I'll tell you what to do. So we want, as Kiana says, we want 3 standard deviations, do we not? We don't want 1 deviation, we want 3 deviations. So we take 10.4 over the square root of n, and we multiply that by 3. That gives us 3. Mariah, the reason we get 3 is because we know that 99.7% of the population corresponds to 3 standard deviations. That's where the 0.997 comes into play. 99.7% means 3 deviations. And we want 3 deviations to equal what? How much is 3 deviations according to this problem? No. 99.7% of the data falls within 3 deviations. Now, 99.7% of the data falls within 3 deviations. Each deviation is 10.4 over the square root of n. So if I take 3 deviations, I will get a distance. I want that distance to be something in this problem. They tell me what I want it to be. They say, we want this to be equal to a specific value. What is that specific value? Read the question. They tell me. They say, we want it to be, no, because you can never guess the mean. No, but I see where you got that from. We want it to equal 1. We want 3 deviations to equal 1. Yes, Ingrid, yes. We want no more than 1 point away. We want it to be 1. That's exactly it. We want 99.7% of the data to be within 1 point. 99.7% is 3 deviations. So we want 3 deviations to be within 1 point. So 3 deviations that way, 1 point away, another one. God damn it, I'm full.
It's the last one.
Okay. We want 3 deviations that way. We want 3. Oh, yes, Jesus. Oh, he just keeps bringing me food. What can I do? I just got to eat it, right? Got to eat it. I know, that was a joke. That was a joke. That's why I said it. So what we have here is that 3 times 10.4 3 times 10.4 over the square root of n is equal to 1. Let's solve for n. How do I solve this for n? I know it was a joke, okay? I was trying to be funny. You're supposed to laugh. Nobody did. Well, Anthony did LOL. That's good. But he could have LOL'd Mariah's comment. So I don't even know if he was LOLing my comment, which makes me very self-conscious right now. That's all I can say. But nevertheless, what do I do now? 3 times 10.4, smirking in silence is fine. I can handle that. 3 times 10.4 over the square root of n is equal to 1. How do I solve this for n? How's your math? I laugh with the mic off. That's fine. I can handle that. I'll just assume that everyone was laughing silently, or in Weston's case, smirking. So 3 times 10.4 over the square root of n is equal to 1. If I get the square root of n to the other side, I get 31.2 equals the square root of n. Once I have 31.2 equal the square root of n, what do I do next? Square it. So I get n equals 973.44. But I can't ask 973.44 people, can I? So how many people do I ask? Excellent. You always ask more. Because 973.44 is perfect. If I ask fewer than that, my error is going to be bigger. If I ask more than that, my error is going to be smaller. I don't mind having a smaller error. So my answer is 974. And there it is. N equals 974. Let's look at their explanation. Maybe mine sucked and theirs is better. 99.7% of all observations fall within 3 deviations. So we want 3 sigma over the square root of n to be equal to 1. And then you solve for n. So that's basically exactly what I wrote down. Does that make sense? Are there questions on it? Remember, first of all, just be aware that, online learning is tough in general. Second of all, statistics. has its own complications because you're looking at things in ways that you've never really looked at them before. Third, that's basically it, those two things. Oh, well, third is a general idea that it's very rare that you go to class, you pay attention, you get it, you walk out, and it's internalized. Quite often, have you ever had this experience where you go to, especially math, right? You're in class, you're following along, and you're like, oh yeah, okay, I get that. And then the teacher says, okay, now you do one, and you're like, wait, what did he do first? Right? We think we get it because we followed along when someone else did it. And then it's our turn, and all of a sudden it's like, wait, I don't know what to do. That's pretty much every class that I ever took in my entire life, right? Right, exactly. You think you got it, then you do the homework and you start questioning everything. Okay. Well, Launchpad might be hard, but this is not, unique to this class. Let me give you a quick story because it'll take away from learning time, so nobody's going to complain. I had a professor in physics my first year. I was a student at CSUN. This is back in 15 years ago when I was a student here. And I took a guy, his name was Paul Lee. He's retired now. But Paul Lee was I thought he was arguably the most brilliant teacher I've ever had. He went to Caltech. I don't know if you guys know about Caltech. It is generally regarded as the #1 school for theoretical physics in the world. MIT for applied and Caltech for theoretical. And his instructor was Richard Feynman. If you've ever heard of Richard Feynman was a Nobel Prize winner and considered one of the greatest physics teachers of all time. And so you have a combination of an amazing teacher, an amazingly brilliant student. And he said that he would go to class and he would get it, and then he would sit down to do the homework and he would have no idea what to do. So this is not me and you and stats. This is everyone who's ever taught and everyone who's ever been a student and every class that's ever existed. This is how learning goes. You go to class, you hopefully pay attention and take notes. Sometimes you don't. That's even worse, but let's give you the benefit of the doubt. You go to class, you pay attention, you think you got it, then you go home, you sit down to do work, and you realize that you don't have it. That's everyone. The wise words of Berkowitz. Yes, on my tombstone. That should be my expression. You don't have it. You might think you have it, but you don't have it, or something like that. Or where did that steamroller come from? I don't know, something like that. But anyways, the point is that where does true learning come from? It doesn't come from your teacher in class, because no matter how good your teacher is and no matter how good you are, that doesn't stick. The true learning comes from the struggle of trying to figure out the homework on your own, which is why we give you homework. Because you sit down to do the homework, you realize you don't have it as well as you thought you did. You struggle, you figure it out. That's where the aha moments come in, and you leave knowing it. Good homework is not so easy that you don't learn, and it's not so hard that it's just you give up. There's a sweet spot of just hard enough where you struggle to get it and then you get it. Okay, that's what homework should be. And sometimes, you're all different. Some are better than others. We all have the same homework, so you're not always going to have it in that sweet spot. But that's really the goal. That's really how you learn. So many people feel that the point of homework is to get the answer. So they look things up online, or they ask their friends, or they get a tutor, which is all fine. I mean, getting the answer is great. But if you don't yourself struggle to figure out the problems, you will not learn them. And, we're college students. We like to party and stuff. We like to procrastinate and do other things. And then homework is due tomorrow, so we panic and we borrow from someone and we hand it in and we say, oh yeah, we got it. Partying during COVID. I don't know how you party, but my parties are all alone, so usually it ends up with me being in a fetal position on the floor, sucking my thumb or something like that. But, that's the best way to party in my mind. Anyway, the point is, is that this stuff should be hard, but not too hard, because if it's so easy that you don't learn, then you're not learning. Anyway, that was my little spiel. Hopefully, I needed that talk. Good. I'm glad. Because hopefully you take it to heart that it's not supposed to be easy. Okay, it's supposed to be challenging. Not so challenging that you give up, but challenging that you learn. And I might be good at this as teaching. I might not be. I like to think I am, but then again, I've never really done this online thing, so maybe I'm just not good at this particular format. No, it's okay. I'm not trying to look for praise or anything like that. My point is that I've always thought I was a good explainer, but this format I recognize as being very difficult, both on my end and on your end. But here's the thing. Have you ever had a teacher that you couldn't understand? Maybe they had a bad accent or just so smart they were talking over your head and you had no idea what they were talking about? Has anyone ever had that? So you've had that before, right? Not all of you, but some of you. At the end of the day, whose responsibility is it for you to learn? It's not the teacher's, right? It's yours, right? At the end of the day, it's your responsibility. So you can have a great teacher or a bad teacher, but at the end of the day, it's your responsibility. So if you're having difficulty here and it's just not working with me in a large classroom of 40-something people, you can come to my office hours, which very few of you have done. You can go to Tutoring Center, which exists. There are videos online, some better than others. But if you're going, I don't get the central limit theorem, then go to YouTube and find one of a million videos on the central limit theorem and see if someone out there could explain it in a way that clicks for you. I've certainly had teachers that I had in the past, and some lessons I got, some lessons I didn't. And sometimes I get it from somewhere else. And it's like, oh, yeah, I get it now. Oh, that's what he was trying to say, and he just couldn't get the point across. It happens. Well, okay. Khan Academy certainly means well. It's a great program for the basics. But if you want to get a if you want to get a deeper understanding, Khan Academy is not the place to be. But if you just want to get the basics, and it's a good starting point, get the basics and then move on. There's nothing wrong with Khan Academy or all the other videos that are out there. I have never, I think, not answered a question in class. I might have said, give me a few minutes, so let me finish something first, but I will never block you for asking me really dumb questions. I might block you for asking me intrusive questions, but favorite food, there's no question about it. Those are orange creamsicles. So Tutoring Center is great, just way too packed. I understand that. A lot of people need help. If my office hours are not working for you, or you feel that you would like some individual attention, we can always hop on a Zoom meeting over the weekend. I'm around all the time. Just, it's so good, Sydney. It's so good. You just don't understand. Okay. Anyway, I do want to start chapter 16. So that's my little spiel for the day. I hope you take it to heart. Let's look. You know what? It's already 7:40. I need a break. We'll stop here. We don't have to go on. I'm going to stop sharing now. And